Okay, now let us talk about the crystallinity of polymers. The crystalline nature of substances can be identified from the X-ray diffraction pattern of these substances. The X-ray diffraction pattern of polymers gives sharp as well as diffused patterns. So the sharp patterns indicate that the polymer molecule exists as a crystalline substance. At the same time, diffused patterns are also there. That means the substance exists in a less crystalline nature. So here in polymers, we can say it exists as an amorphous substance. So the same compound or the same polymer will give these two type of patterns, that is sharp as well as diffuse patterns. We can say in polymers, crystalline and amorphous nature coexist. So there are some regions which are more crystalline in polymer, and there are some particular regions which act as more amorphous in nature. So crystallinity and amorphous nature coexist in polymers. So we can say the overall property, let the overall property be Q, then the overall property of a polymer can be written as QC plus QA. Overall property is the sum of crystalline nature and the amorphous nature. So QC is the crystalline component, QC crystalline component, and the QA is amorphous component. So from this we can say the properties like density, Young's modulus, permeability, heat capacity, etc. lies between crystals and the amorphous substance. That means density of polymer substances are greater than amorphous substance but lesser than crystalline substance. That is lies between these two. And all these properties are like this. And about permeability of amorphous substances are more than crystalline substances. So here for polymers, permeability is greater than crystalline substances and lesser than amorphous substances. So if we talk about Young's modulus also, so here in y-axis Young's modulus, and in x-axis if we plot percentage of crystallinity, we'll get a graph like this, that is a steep rise like this. If percentage of crystallinity increases, then Young's modulus increases steeply. Here for polymer molecule, the Young's modulus lies between crystals and amorphous substance. And the degree of crystallinity of polymer molecule can express in terms of 1. Density, then mass, then in terms of enthalpy. So in terms of density, we can write it as
degree of crystallinity XV equal to
d minus dA divided by dC minus dA. Here d is the density of the sample and dA is the density of amorphous region and dC is the density of crystalline polymer. Same way, in terms of mass, we can write it as xm equal to V minus VA divided by VA minus VC. And here V is the specific volume of the sample and VA is the specific volume of amorphous region and VC is the specific volume of crystalline substance. Same way, in terms of enthalpy, we can write it as degree of crystallinity in terms of enthalpy equal to H minus HA divided by HA minus HC, where H is the enthalpy of the sample, HA is the enthalpy of amorphous substance and HC is the enthalpy of crystalline substance. Then factors influencing crystallinity. So we can say structural regularity, is an important factor which influences the crystallinity of polymers. So if the polymer is more regular in its structure, then it is crystalline. Right, if it is irregular, it is less crystalline. Or we can say if the polymer is symmetric or stereoregular, then these are crystalline in nature. If it is less symmetric and non-stereoregular, then it is less crystalline in nature. That is, amorphous nature is more in that polymer molecule. Same way, if the polymer is linear, then it is crystalline. And branching reduce the crystallinity. So if branching increases, it will become more amorphous. For example, polyethylene is about 90% crystalline. But if branching is there, relatively high branching reduces its crystallinity into about 40%. Then the second factor is polarity. The presence of polar groups normally increases the crystallinity. For example, nylon 6. Some polar groups are there and the interactions such as hydrogen bonding in the polymer molecule increases its crystalline nature. And the next factor is side chain. So in some particular polymers, presence of some small side chains increases its crystallinity. The best example is polyvinyl alcohol. So basic structure is this: CH2, CHOH, CH2, CHOH. So we can write it as N times. So this is the basic structure of polyvinyl alcohol. The presence of this OH group increases the structural regularity, and hence the polyvinyl alcohol becomes more crystalline. So these are the factors which influence crystallinity of polymers. Then I am going to wind up this section by explaining one more term, that is crystallizability. This is the maximum crystallinity a polymer can achieve at a particular temperature. So it is the crystallizability means it is the maximum crystallinity a polymer can achieve at a particular temperature. So this is all about the crystallinity of polymers.